In this part, we're going to introduce the concept of the inflationary universe and look at the consequences of having the cosmic microwave background and what that helps us understand about the universe. So with that, we're going to start studying the shape of the universe again, because the CMB gives us a wonderful tool to test the geometry of the universe. And what I'm going to go through right now is a build-up of what do I mean by the geometry, and then we'll show these strange pictures. So I'm going to start off with is consider two parallel rays. All right, I have two rays, and they just go off to infinity like that. And the question is, will these rays ever intersect? If this one keeps going and this one keeps going, will they ever cross? And these are just mathematical objects. We're not talking about, dark matter halo or a black hole bending their paths. I'm literally just saying, take space-time, will these continue on forever parallel? And our intuition says definitely not. Like, the definition of parallel rays are things that are parallel everywhere. But, all right, this is where we gotta start thinking in the strange abstractness of the cosmos. What if the shape of the universe curves? Think about it. We live on this big, massive planet, and it's so big that in our perspectives, a lot of people sometimes will say it looks flat. And yet we know for a fact that's a curved, we live on this sphere. So imagine things on the big galactic scales. What kind of curvature could exist that we barely can detect or understand? And so these ideas of shooting out parallel rays and seeing where they go give us at least three pictures that I'll go through of different possible paths for those two rays that I initially shot out there. The first one is the one that we have a more of an intuition of, and it would be what's called flat space-time. I shoot out two parallel rays, and they will stay parallel forever. But it's totally plausible for the universe to be in what's called a spherical space-time, or the actual curvature of space-time will eventually cause them to intersect. Another possibility is that they diverge. Sure, these two will never cross, but in our Euclidean sense of being parallel, they no longer are because they go away from each other. So this is the zoomed in perspective of what it's like if I shot a laser, and saw which way they went. What is the curvature of space-time itself? And so I'm going to pull back material from our previous section and say, remember that density parameter, that omega. The density parameter is a factor that determines what the shape of the universe is. You could have a flat universe where the sum of the density parameters from matter and dark matter and the sum of the dark energy is exactly 1. And in that case, we'd say we live in a flat universe. We shoot parallel rays, and they stay parallel. If the density parameter is greater than 1 in total, then that's a universe where eventually there will be enough gravitational force to crush the universe back in on itself. The universe will have been birthed from a Big Bang and eventually crash back into itself, going back into a new singularity. Or you have these crazy cases where the universe is infinite in size and expanding at even greater and greater rates. And so it's diverging, blowing away, getting away from each other. So let's now pull back in that cosmic microwave background to test this. We look at density fluctuations, specifically our best map, one of our better maps, is the Wilkinson Microwave Entropy Probe, the W map. And so you look across, this is about a 25-degree angle, and at different sections of the CMB, we can see sections that support a flat universe. We can see some sections that might imply what's called a saddle or a hyperbolic. and others that suggest the collapsing universe. So you might recall from section 21 how I spoke about how we've measured the density parameter and it's like 1 plus or minus a tiny amount. Pictures like these are how we got that figure, that estimate. So we know the universe is probably flat. It's probably a flat universe. But this ties into this horizon problem and the name of this section, this inflationary universe. If the universe's geometry is going to be exactly flat, well, that requires that the density parameter of the universe is exactly 1. Not 1.000001. 1. Exactly. Even the smallest deviation from 1 at the very beginning of the universe would have been magnified over extreme magnitudes because of the expansion rate of the universe. So a small fluctuation would have been blown out, and these fluctuations would then mean that the universe should not be homogeneous. It wouldn't see the homogeny that we observe today. So physicists are trying to get an explanation for this. How is it that we have a universe that's so homogeneous when if it is not exactly 1, this density parameter, you wouldn't have homogeneity? And the solution, well, first off, this is called the horizon problem. How can we have a homogeneous universe if a small, even minute fraction of a fluctuation in the density would not lead to a homogeneous universe? And the solution is what we call this inflationary hypothesis. Right? Basically, you say, look at the universe, right? And you're looking at seconds after it. So this is fractions of seconds, about 10 to the minus 35th seconds after the Big Bang, whatever that was. About 10 to 35 seconds after the Big Bang, something caused the universe to suddenly blow up in size. The universe suddenly just swelled up like a balloon, inflating rapidly. And this inflationary model does explain things like the flatness of the universe and the homogeny. By having the universe rapidly swell up in size in a short time span, you can get a universe with small fluctuations. Coming back to my ants. Imagine you're on this balloon and there's little pucks here, little divs or a little bit of dirt, and then suddenly the balloon just poof, inflated significant orders of magnitude, and now the curvature seems to have been flattened out. So the inflationary hypothesis is a tool trying to explain the observed fluctuations and get a still homogeneous universe.